What is ray reversibility? Well, it says light retraces its exact path. And talking about evidence, here's evidence for you. Look in a mirror, and you'll see that straight ahead, the mirror sees you, and you see the mirror at the same time almost. Almost, you could probably draw, if you had a string, you could take eye to eye, and it would be a straight line. And if you can see the mirror, but the guy in the mirror can see you, in fact, that's what happens when you see someone in front of you. You see their eye, they see your eye, and you're kind of looking on the same axis. How can that possibly be in quantum mechanics where you have little particles going back and forth? Okay, but I'm getting ahead of myself. This is where it starts. It starts with Mr. Heron, also known as Hero of Alexandria. Okay, and he lived in the first century of the Christian era. He came up with a notion which was quite startling for his age, and that is that light takes the shortest path. Meaning what? Straight line. Light travels in straight lines. Something that Mr. Newton defended to the end of his days. Okay? He didn't like the wave thing because waves go up and down. And Newton said, no, there's no up and down. Light travels straight. And this fellow said the same thing. Light travels straight. It says if a ray of light propagates from point A to point B within the same medium, the path length followed is the shortest possible. Okay, so that's the principle that Heron came up with. Okay, from there we can take a big jump, maybe almost 1,000 years, and we come to this fellow. His name is Alhazen, Arab guy from Iraq, and he discovered what is known today as Snell's law. He discovered these angles, especially he was studying the eye. He wanted to know how the eye worked, so he wrote his book, Book of Optics. Did a lot of study there, more for doctors. Okay? He studied the eye in quite a bit of detail. That's an impressive book for the time that he lived, which was the first millennium. The form, and he wrote this, the form that reaches from the visible object to the eye's surface passes through the transparency of the eye's tonics, for it is among the properties of transparency that the forms of light and color pass through it and continue what? Rectilinearly. He's thinking about particles traveling in a straight line. So he's talking about rectilinearly, rectilinear travel. Rectilinear is a verb. It's an adverb. It qualifies motion. Straight is an adjective. It qualifies a noun. In other words, if you can have a straight ruler, okay, you can talk about that. That's different than talking about rectilinear motion. That is an adverb in that because it's qualifying a verb. And what he's saying is he's thinking of particles. Okay, that's all we ever thought about, particles, until Mr. Robert Hooke came up in 1665 with the notion of the wave. And it wasn't a transverse wave, but he was thinking of waves. That's what he saw through this microscope. So he wrote about it in his Micrographia book, 1665. Anyways, it says, if all transparent objects were to be tested, it would be found that light will extend through them only in what? Straight lines. So he's talking about extending straight lines and traveling rectilinearly. Okay, so make up your mind, Mr. Alhazen. Does light extend in a straight line? Does it travel rectilinearly, like with a bunch of little corpuscles? And why would they travel rectilinearly? Okay, and the reason I'm asking that is the Earth is moving, isn't it? Well, unless you're a flat earther, yeah, you don't believe that. But in general, most people out there think that the Earth is moving around the sun, and if that's the case, we're moving constantly. And here are all these corpuscles, particles. They should never travel in a straight line. Okay, so even if I point my laser pointer, the Earth is moving. So, the beam doesn't not remain straight if it's made out of discrete entities. They should form even as small as you can imagine it, but it should form a curve. Okay, you can't get a straight line when the thing you're on is moving. Okay, it moves to some degree. If you're moving to the right and you got a bunch of balls coming out, they're going to form a little arc. Okay, so this is the problem, and that's not the case with light. Light travels rectilinearly, extends straight, whichever one you want to use, but it's got to be a straight line. It's got to be rectilinear. You can't do that with discrete particles if they're flowing. Okay, so this is the issue. Okay, visual sensation of the light and color in a visible object is due to a form coming from that visible object to the eye. He's the guy who discovered, or at least the first one who wrote about something against Aristotle, especially Euclid, that they thought the eye emitted particles, and that's why we see, because light came out of the eyes. And Alhazen corrected them, says, no, no, light comes from the object to us. Okay? Under the rope model, it goes both ways. It comes out and it goes in both ways, both directions, simultaneously. That's what's good about the rope model. Anyways, we continue a few more years, 600 more years. We arrived at this gentleman, Pierre de Fermat, and he came up with Fermat's principle. Essentially, he's repackaged Heron's principle. And he says the path taken by a ray between two given points in the path that can be traversed in the least time. Came up with the least amount of time. Okay, and again, he based it on what is known today as Snell's law, a Dutch fellow who apparently came up with the equation, but this equation I think was known even before Snell. Snell kind of found out about it, or maybe he recalculated, maybe he reinvented the wheel, and today he's given credit for Snell's law, which is the angles of refraction specifically. Okay, he was able to calculate that angle. And again, the reason he can calculate an angle is because light either extends straight or travels rectilinearly, no deviation whatsoever, as Mr. Newton defended later on, a few years after these folks. Okay, so that's where we are by the 17th century. Okay, eventually they found out that light not only travels straight or extends, travels rectilinearly or extends straight, right? Let's keep the language straight here, but it retraces its path. It goes and comes along the same path that it went. And that's what's known as the principle of ray reversibility, amply used in optics today. All opticians know about ray reversibility. Great. So now how do we explain that? How do we simulate that with particles when the Earth is moving around the sun? We have motion. We're moving with respect to everything in the universe. And here these series of photons, they travel straight. And you might say, well, I know, Bill, you're so close to the mirror, light travels at 300,000 kilometers per second. It's so fast that for all practical purposes, it's traveling straight, right? Or extending straight. Really, they call it, traveling rectilinearly. That's what we should say. And it comes back along the same path because it moves much faster than the Earth moves. Okay, so let's do it a little longer. Let's find out what happens when we stretch the path and get feedback, get light coming back. And it's got to do with this. Let me just show, this is just showing the principle of ray reversibility again. Light retraces its path. We discovered that, okay? And so we live with that. Opticians, they live with this, okay? Well, what's the issue? Here's, 1971, Apollo 14. Before that, Apollo 11, later on, Apollo 15 did the same thing. They put what is known as a retroreflector on the moon. And they shoot this laser, okay, from the Earth, very powerful laser that reaches, touches the retroreflector on the moon and comes back to Earth to our computers, and we are able to see a blip. Okay. Now the beam that goes out is extremely powerful. The beam that comes back consists of only a few photons, a handful of photons. Okay, so we don't get what we sent out, but the important thing is, according to these people, is that we're getting a reflection from the retroreflector on the moon, and by the time it reaches Earth, a lot of these photons get sidetracked somewhere, but 2 or 3 or 25 or whatever come back to the detector on Earth, and we are able to map that on a computer. Okay, so that's what this is about. And the main reason they did this is not to find out, how fast light travels. That's probably one issue. But they wanted to find out whether the moon was getting closer or moving farther away from us. That's the point of, that's why it's called the lunar ranging experiment. Okay, and this is the retroreflector that was put on the moon. Okay, Apollo 14. Yeah, here you have the astronaut putting the retroreflector there, and what it looks like today. Okay, so from the Earth, they shine against this retroreflector and get a beam back, and essentially what arrives on Earth is just a few photons. Okay, or that's the explanation, because it's a very weak beam that they receive back. Okay, how does quantum mechanics explain this? Okay, here's the laser ranging in action. Okay, they point it at the moon. And these people say that that gazillions of photons go, but only a few, okay, a couple of photons return. And because that's what light is supposed to be, right? Just a flow of photons, of discrete particles, corpuscles, which are not really corpuscles, they're just equations, but that's how they simulate it. They say, well, yeah, it's discrete. The little ball, you got to think of them as little balls, and we shoot them at the moon, and they come back. You know, gazillions go out, and a handful come back. Okay, that's how they do this, or that's how they explain it. That's the explanation, the mechanism that we have today from quantum mechanics. But we have a little problem with this because, you know, here we have the Earth, and the Earth really goes around the sun. Let me make this a little bigger here. Okay, you know, here's the retroreflector. Put this over here. Okay, we have round trip. It's almost 2.5 seconds. Okay, but see, the Earth moves and the moon moves around the Earth. The Earth moves around the sun at 30 kilometers per second, and the moon moves around the Earth 1 kilometer per second. Okay, so we got a little bit of problem here because we're saying, hold it, we shoot these photons, these loose particles, and they have to form a curve because, you know, everything's moving. Okay, and then out of they bounce off the retroreflector, come back. They have to come back to the Earth where the Earth is now. It's moved already, you know, approximately 75 kilometers. And, you know, the question is this feasible considering because we got to put something else on top of that, and that's general relativity. General relativity says that space is warped around any celestial object. So not only do we have the curvature of motion created by motion, but we have the curvature of space-time itself that these photons are falling into. You know, they're falling into the, they're not traveling straight. They're not traveling rectilinearly. They're falling into this hole, which is created by both the moon on its side and the Earth on our side. How is it that any photons come back? Okay, so keep this in mind. This is one of the big problems that I see with their explanation. Okay, let's get these out of here. Okay, how does the rope explain this? Just so that you have a comparison. We're saying that, well, you know, all we have is just straight line to the moon. There's gazillions of ropes. Okay, I'm just putting one there, but essentially, you know, the laser is just a high frequency, okay, short length rope. It reaches the retroreflector, and along that same rope, you get the signal back. Okay, that's it, and that's why they get a blip on their chart on their computer. Okay, so we're just saying that that's what's happening. Okay, and we can also answer why the moon doesn't fly away, because we're saying every atom of the moon is bound to every atom on Earth. So we can explain that, something that quantum cannot explain. Here's the quantum version. You know, why does the moon go around the Earth and not fly away if nothing is connecting the Earth to the moon? Okay, how do you explain this with particles? You might say, well, we explain warp space, warp time. Well, what do you mean warp time? What kind of explanation is that? What physical interpretation is to say that you do it with warp time? So again, just because we cannot see the interconnection between the Earth and the moon does not mean that there's nothing there. Okay, that's the issue. And here's the same moon orbit with the rope. Okay, so you can see it there. You can see why it's going around, because every atom of the moon is tied to every atom of the sun. It's just that we cannot see or touch these mediators, which I call the electromagnetic ropes. Okay, so this is our explanation. And we have an explanation, at least a physical interpretation. Quantum does not. That's my point. Okay, we can do it with the Earth orbiting and the moon orbiting. Okay, here we see the Earth is tied. And so it doesn't matter where the moon goes. If every atom from the moon is attached to us, and that white big line there, that represents the beam that's going to the retroreflector. So, you know, the moon can go anywhere it wants. We'll always find it because we're connected with all these ropes. And then there's one set of ropes, again, it's a set, that connects the emitter with the receptor on the moon. And along those same ropes is where the light comes back to us, obviously at a different frequency. Okay, so we have an explanation for both, not only for the retroreflector, the lunar ranging experiment, but also for why the moon doesn't fly away. And on the other hand, quantum mechanics, together with general relativity, have no explanation for either phenomena. Okay, because you're going to have to really go out of your way to be able to explain why photons come back to Earth, especially through warp space, and especially when both the moon and the Earth moved, constantly in motion. So I'm not sure how they're going to get any photons back. Why would they? Okay. Okay, a bigger problem that I see is the following, okay, and that's this one, and that's that. Imagine the Earth and the Moon are moving, right? So the Moon is going to move. It moves 1 kilometer per second. Light travels 300,000 kilometers per second. Okay, keep those numbers. Light travels fast, the Moon goes slow, but the Moon moves. It's not instantaneous where you can shoot photons from the Earth directly at the Moon where the Moon is now. You got to shoot the photons where the Moon is going to be 1 second later, because it takes the light 1 second, really a little more than a second, to get to the Moon, okay? And by that time, the Moon ain't there anymore. The Moon is 1 kilometer farther down the line around the Earth, but the Earth also moved 30 kilometers, so the Moon is not there anymore, okay? And here I try to illustrate that you got to point to where the Moon is going to be, not where the Moon is. And so the question is this what they do? Are they pointing at where the Moon is going to be in 1 second, 1+ second, because it's more than 1 light second away from us? No, they point it directly at the retroreflector. How can they do that if the Moon is moving, unless the retroreflector atoms are connected directly with the source of the laser? That's the issue. So here they have to point at where the Moon is going to be in a little while. And yeah, that's not what they do. And again, they handle this all through computers and so on, so they don't know what they're doing. All they know is that, oh, we're getting some photons back, and that's their explanation. But if you ask them why, how is it that you're getting photons back, they can't give you an answer. You know, they say we just do. We send gazillions and we get 25 back. Great. What are my conclusions here? Okay, I'm saying that ray reversibility, light retraces its path, its exact path. Okay, how does quantum explain this phenomenon in discrete particles? And the problem is that the Earth, as well as the Moon, they move, constantly move. So first, not only are you sending it in an arc, because it's not completely a straight line, you can never get, if the Earth is moving through space, you're not going to have the sequence of photons traveling exactly in a straight line. Okay, they have to curve. Then you got to shoot them where the Moon's going to be in a little while, and the Moon is moving 1 kilometer per second. The Earth is moving 30 kilometers per second, so neither one is where it used to be. They're both way off. And so you got to shoot the photons where the Moon is going to be. You got to shoot them in the middle of space. That's not what they do. They point it directly at the Moon, and they point it approximately in the region where they left, because they have that map. They point it where the retroreflector is at. How is it that they can shoot the laser directly at the retroreflector if the retroreflector is no longer there as soon as they press the button to shoot the laser? The Moon, the retroreflector, the Earth, everything move. They have to shoot it where it's going to be in 1 second, more than 1 second, it's like 1 1/4 seconds. Okay, so this is the problem. And then lunar ranging experiment makes it impossible for light to consist of discrete particles. It debunks the quantum version of light, because quantum cannot explain it rationally. Not because I don't believe in it. That's not the debunking. The debunking is that it's an irrational explanation. You cannot explain the lunar ranging with particles. Okay, they do so because they want to, but they have no way of justifying how this is possible. Okay, especially when general relativity holds that space is warped in the vicinity of all celestial objects. Both the Moon weighs space and time. It's weighing down time. Here on Earth, we weigh time down. Space-time is curved, but we get the photons anyway. And by the way, the Sun is also warping both the space underneath the Earth and the Moon, whichever way you can imagine that. Okay. Corollary: ray reversibility falsifies the discrete particle hypothesis of quantum mechanics, if we're going to use that word falsify. By falsify, in this case, I don't mean we've proven or disproven or anything like that. I'm saying it's irrational. You simply cannot explain it by assuming that light consists of particles.